The topic of today's webinar is the audio analysis of smart devices. I will let you know the meaning of smart devices within a few moments. But just for the time being, we will of course talk about challenges of these testings. We will talk about the test itself, the preparations, the measurements, and we will provide some application hints. But first, let me introduce myself. My name is Markus Becker. I'm the technical director here at NTI Audio. And sitting next to me is Schmidle, our product manager. He is assisting me during the webinar and he will take care of your questions. The topics that we have prepared for you are a first overview, introduction to the issue of smart device testing. We will talk about the necessary preparations. We have also prepared a practical presentation for you. And of course, as mentioned, we will provide some application hints. At the end, we will answer, or maybe even during the webinar, answer to your questions and give you some auxiliary information. The overall duration of the webinar today would be around 30 minutes. What do we mean by smart devices? Basically, we mean electroacoustic gadgets or systems that can replay music or speech, for instance, pre-recorded announcement or songs, whatever. This can be, of course, MP3 players, smartphones, tablets, but also PA systems, public address systems in train station, for instance, or navigation systems in your car. Or maybe if we talk about a little bit older devices like CD players, answering machines, tape recorders, all items that are able to replay a sound, signal, speech, or music. What's the key challenges of testing these devices? Number one is we need a solution to evaluate the audio quality of the device. So we could of course just listen to the output of these devices, but as you all know, listening is a subjective test and that is hardly reproducible, and it does not really give us accurate feedback on the performance. So we really want to measure it accurately and reliably, the performance, whether the behavior of the tested device complies to the specifications. The second key challenge is connected to the lack of an input connector in most of these devices. What does that mean? Let's have a short look on the left side here on this schematic picture. A typical audio test setup comprises the audio analyzer, which has a built-in generator. The generator creates the test signal, which is transmitted through the device under test, comes back to the internal analyzer and is analyzed in there. Normally, the analyzer has also a link to the generator so that the analyzer part knows, for instance, when the test signal has been sent out and it can synchronize to it. However, in our application, this is not the case. Because of the lack of this input connector, we cannot directly feed the test signal into the device under test, or especially through the device under test. So what we have to do is we have to somehow transfer the test signal to the internal memory of our sample and then replay it from that internal memory and send it and link it to the test instrument analyzer. And when doing that, of course, we have to make sure that the triggering, the initiation of the test signal replay and the start of the signal acquisition are synchronized to each other, that they happen at the same time. So these are the two key challenges: transfer of the test signal and correct triggering and synchronization of the test signal to the analyzer. Now, when we talk about testing, of course, we have to select a proper test signal. And there are some requirements that we should keep in mind and try to satisfy. The one is the bandwidth. Normally, we want to measure several frequencies. We want to make sure that the sample we are testing meets the specifications at various points in the spectrum. Secondly, we are of course very interested in executing relevant measurements that really describe correctly the behavior of the device under test. We don't want to miss any important behavior or defects from the device under test. Third point is the test should not last too long, especially when we're talking about production applications. You know, we have little time in a mass production. 1 second is a typical target goal, but could even be less. And last but not least, the overall handling should be simple, should be feasible and applicable even by not highly skilled technicians. It should be simple to set up the test and execute it and still be stable. Now there are 4 solutions, typical solutions that are selected. The oldest one would be just a sine wave at a specific frequency. This is pretty simple to realize, of course, but on the other side it suffers under a huge lag, and that is the lack of relevance. Just testing just one frequency gives only a very small glimpse on the behavior of our sample. It does not cover a bandwidth or several frequencies, so it's just a very simple test that is not really very significant. Of course, we could transmit several sine waves with different frequencies one after the other, so we are ending up at the stepped sweep, which is symbolized by this picture. Step sweep provides actually relevant results. It's a very proven method. However, it has the disadvantage that it takes quite a long time because the analyzer has to synchronize every time to each transmitted frequency, and that takes time. So the overall test time is in the range of several seconds, typically. Then there is a third approach, the multitone testing. In a multitone, I am combining several sine waves with different frequencies into one burst. So this is a superposition of several sine signals, and it has the huge advantage that I can keep this burst pretty short, so I can really achieve a high speed of my test. But on the other side, the disadvantage is that multitone testing is rather complex, and it needs a profound understanding and experience of the interpretation of the test results. I cannot directly one-to-one compare a frequency response from a multitone, for instance, with a step sweep analysis. There are slight discrepancies, and I have to be aware of that. Or the sine waves in that multitone burst would cause some intermodulations, which have to be considered as well. Fortunately, there is a very nice and very powerful solution to our demand, and that is the glide sweep. The glide sweep is actually a sine wave that continuously changes its frequency. So by that, we are covering a wide frequency range, the one that we are looking for. We can do that within a very short time. 1 second is a easily feasible duration. The test results can be interpreted straightforward, directly compared to conventional measurements like step sweep measurements, and of course they are highly relevant. So this is a solution we are looking for, and we are actually applying in our setup here. The next topic we have to keep in mind is the signal acquisition. So here we have to consider 2 things. The first is the input range, or the sensitivity of the analyzing test instrument. Just to visualize that, if you look at this red signal, this would be our incoming test signal. If we adjust the input range of our analyzer too wide, or pretty wide, which is represented by these yellow dotted lines, we would lose a lot of dynamic range, and loss of dynamic range means less accurate test results, measurement results. If we on the other side would do it too tight, if we would adjust the input range too tight, there would be some clipping. You see these peaks of the test signal, they would clip with this tight input range, and that would of course falsify our measurements definitely, and unwanted. So the solution is that we have to carefully adjust the input range in a way that it covers the whole level range of the test signal, but is not too wide. And the second challenge is that we must make sure that our analyzer triggers correctly and exactly to the starting point of the test signal. We don't want to lose some milliseconds, for instance, where the analyzer would need to wake up. No, we really want to be ready from the very first moment, even if there is a certain time before the test signal comes in. So fortunately, we have of course foreseen that in our system, that it is very fast, actually, and really in real time able to sample the very first signal components coming in. Now, if we look at the whole test procedure. It looks like that. We have the test instrument, which is possibly creating the test signal, or that can also be done on the PC. And from there, the test signal is transferred as a file to the internal memory of our device under test. From there, it is then replayed through the internal replay circuit, for instance, to a speaker, but it could also be an electrical output. In this case, it's a speaker, a built-in speaker, and from there we pick up the sound through a microphone and feed the generated signal back to the analyzing instrument. In here, the incoming signal is analyzed, is calculated, and the test results are, of course, brought back to the host controller. So we have to take care of this signal transfer, of the coupling between the device under test and our input connector. We have to set up our analyzer correctly, and we have to make sure that the initiation of the test itself, the replay of the signal, is done properly. Well, I think it's time to take a look at our presentation. I have here on my test bench a host controller. I have our Flexus FX100 audio analyzer as test instrument. I have a test jig, which has a built-in measuring microphone, and as a device under test, I'm using just a smartphone. So I just switched over to the FX Control software that is controlling the FX100 audio analyzer. And what you see here is the so-called hardware and wiring. This is a representation of the test setup. I have prepared that before this webinar. So I have actually added these items here, which represent my device under test. I have placed a microphone and connected it to the input channel 2, as it is the case on the system on my test bench. So by this feature, this hardware wiring, I can make sure that I have really done the correct connections and that I am measuring the correct input channel, for instance. Or just an example, if you look here at the properties of our microphone, I see I have entered here a sensitivity. So this makes sure that my calculated level results are absolutely correct, correctly representing the sound pressure level. Now I switched over to the worksheets view. Here you see I have prepared the generator, the glide sweep generator panel. So these are the parameters, or some of the parameters that I can adjust. I have chosen a logarithmic glide sweep starting from 200 Hertz up to 8 kilohertz. I could, of course, edit these data. I have decided that it should take 1 second. And now by clicking just here on the generate button, you see this pop-up. This pop-up actually allows me to create a WAV file with this glide sweep according to my definition. I can here decide where it should be saved in this directory. And by clicking on the generate button, this is already done. So it has been created now. It is on my hard disk, and I can even replay it. And I'm going to do that so that you can hear already how such a glide sweep would sound. Hope you heard it. So this was my preparation. Now, of course, I have to transfer my test signal from my PC hard disk to the device under test. I have already done that, but I guess you know that this is a simple task. On the analyzer side, I have adjusted the input range of my analyzer. I have selected the external synchronization, meaning that the analyzer does not wait for any generator signal from the internal generator. No, it waits for an external signal to come in. And last but not least, I have prepared some measurement panels, frequency response to distortion measurements at total harmonic distortion plus noise plus a selection of upper harmonics. And here the pure sound panel. Pure sound is a very powerful measurement that allows me to detect irritating defects, irritating signal components, audible imperfections of the test signal. So it tells me whether the replayed signal is really pure and clear and there's no click signal, whatever, or noise in the replayed signal. But enough talking. Let's now execute such a measurement. So I'm just replaying the prepared test signal from my device. First of all, I have to arm the analyzer. It waits now, can be for a very long time until it receives that test signal. So I just replayed it. You see here the frequency response, this solid curve. You see the distortion results and here the pure sound results. Apparently I did not place it correctly in my test jig. That's why I have here failed. These shaded areas behind the curves are the tolerance limits, which I had defined before the test. So I'm going to try it once again. Yeah, that was a better run. You see now all the curves are within the given limits. Just to give you an idea how I defined these limits was a very simple task. I just select my panel, I edit the data, and here you see I can manually adjust the limits as I like. Now, giving you an example of the performance of a pure sound test, I will now run another cycle and now create a kind of a click signal by just ticking my pen on the smartphone during the replay of the glide sweep. You see that here, that was just really a slight tick of a tip of my pen on the display, but I mean, you would hear it, of course, immediately, and you see it has a very high impact on the pure sound, on the steepness result. Here it gives me a failed result, which is absolutely correct, whereas if you look at the distortion, you would not see really a very significant result. So this is a really very powerful mean to verify the correct operation of your device under test. Let's get back to our presentation. I want to give you some application hints. Please note there is of course a huge number of application hints I could give you. I just focused on some of them. Others will be presented in future webinars. I will come back to that later. For instance, let's take a look here at the built-in microphone, which might be part of your sample. You want to test that possibly too. So you just would have to apply an external speaker, which is directed towards this microphone, and then you just make sure that, for instance, this replayed, that the test signal that is replayed through this external speaker has to be either saved again on the internal memory and then replayed to the analyzer. Possibly you could even use an internal link between the microphone and, for instance, the headphone jack. That depends on the layout and the design of your device under test. Another part of your device which you might want to test is, for instance, a buzzer or a vibration motor. This can, of course, also be done. And as a sensor, we are using either, again, a microphone or a vibration sensor, which is just connected to the audio analyzer. So we just make sure that this item is doing its operation, is buzzing or vibrating, and then we just measure, for instance, the frequency and the level. So let's talk a little bit about test optimization. This is, of course, especially interesting for those people who have to do this test again and again, for instance, in a production line. So this transfer of the test signal from the PC to the device under test via file transfer is, of course, quite cumbersome and takes time. So possibly, especially when you're going into high volumes, you would rather look that the test signal is already pre-programmed on the internal memory. And that saves, of course, a lot of time. Talking about the measurements, actually, we recommend the 4 measurements we showed to you, or the 3, I have to say. The frequency response, which gives you the feedback, yes, there is a sound coming out of my device. Then the pure sound, which gives you a very significant feedback on the quality, on the clarity of the replayed signal. And the distortion is a more conventional measure, which gives also some feedback. Then the definition of acceptance or tolerance limits is, of course, a huge issue. That will be actually covered by a future webinar. There are lots of different solutions and approaches that might be selected, and we want to present them to you in a separate occasion, because it would just boost the range of this webinar if we would cover all that right now. Talking about the cycle time, and this of course applies especially for production sites when you are fighting for every milliseconds. Yes, there are several means and possibilities to cut down the cycle time, to minimize it without losing relevance, without losing significance of the test, of course. This is a must. And we will explain that to you also in a future webinar. Now, we've been talking a lot about production testing, and there's even one more information or some hints I want to give you, especially when we're talking about acoustical coupling. Keep in mind that ambient noise, which is always present in a production hall, needs to be kept out from our measurement. So how can we do that? There are actually two basic approaches. The one is put the device under test into an anoic box, a shielded box with a built-in microphone, and then you can execute the test. Or if you use what we call a coupler, a closed coupler, this is a metal part with a cavity inside. The microphone looks inside this cavity, and then we have a small opening which we call the sound port, which fits directly to the sound port of our sample, and we have a rubber gasket, so we can press this coupler directly to that sound port, and we have a very direct, very highly repeatable and immune against ambient noise coupling between the sample and the measuring microphone. So this has to, of course, a lot to do with repeatability and reproducibility, which is a very important demand in a production side. Gauge R&R analysis. By the way, all these topics about production testing will also be covered in more detail in a future webinar. And last but not least, again, talking about high volume production, you have possibly several production lines. So one typical challenge is that you define the test on one line and then you just want to copy and paste it to the other lines. You don't want to fine-tune or redefine the tolerance limits, for instance, for each and every line individually. And this is a challenge that can be solved by proper approach, and we will also give you some hints about that in a future occasion. Well, I'm actually at the end of my part. I just wanted to point out that if you have any questions, if you need any support, NTI Audio has a tight network around the world of very experienced and skilled subsidiaries and partners. Here I have just listed our own subsidiaries, but we have many more partner companies in the most important countries in this world who are all willing and ready to support you. But you can, of course, always also ask us if you have any specific question. And here, by the way, this is the link for the replay of this recording, which we will, of course, also send to you as soon as it is available. So let me look about questions that came in. Yes, I see there were some. Yeah, first question is about the bandwidth that can be covered by light sweep testing with our instrument, with the FX100. The answer is it goes from only 5 Hertz up to 80 kilohertz. So this is pretty a wide range and covers, I mean, basically all audio applications. Another question was whether the MP3 or WAV file, I showed you the WAV file, of course we can also generate MP3 files, can be created at different sample rates. Again, the answer is yes. This is a default feature of the FX100. Then a question was whether, yeah, that's a very good question, by the way, whether what happens in a noisy environment, would the analyzer just trigger to a loud signal coming in? The answer is no. We have a very specific design of our test signal. There is a very short header preceding it, and that allows our analyzer to correctly and reliably trigger only if this test signal is coming in. And this header, by the way, also allows us to synchronize the analyzer to the frequency, the core frequency of our test signal. So this is all covered in this application. Then we have another question. Yeah, if that's another good question. If I'm arming my analyzer, I mentioned that shortly, and then I'm waiting for the test signal, is there a certain limitation, let's say 10 seconds or so? No, there is no limitation. The analyzer will really wait as long as the instrument is, of course, switched on and until the test signal with a specific header comes in. And another question I see here was referring to the microphone. Actually, we used our M2010 measuring microphone, which is a very nice device because it's very good priced and compact. but of course you can also use other microphones. You can even use ICP microphones. Both 48 volt phantom power and ICP microphone supply are by default in our test instrument, so you can directly connect the microphone to the analyzer. You do not need any preamplifier, external one or so. Really, you can directly connect it. And by the way, also the other features, the glide sweep analysis is also a default feature that is available with every Flexus analyzer. Only the pure sound measurement, this is an option that has to be purchased separately. So, well, I think this is basically everything. No further questions. So, thank you very much for your attention. I highly appreciated it. And I'm looking forward to see you again for one of our future webinars. You will get, of course, an invitation from us, and of course also the information about where you can replay this recording if you like. So thank you, and goodbye for now, and have a nice day.